Yo, what up guys? This is FRC Coding Class Day 7. Today we're going to be covering motor control, and so this is going to get kind of more into the details of what I would say like is the actual robot programming. So today is motor control, then next week will be writing subsystems, and then code structure, flow, and GitHub the week after, maybe GitHub. Again, this is kind of a fast pace with a little bit longer videos, but again, your feedback is totally fine with me, and we might end up adding a week, a third week after. So we'll have this week, next week, the week after, maybe add another one. I'm going to try to go a little faster than the last one. So basically, motor control, it may seem simple at the beginning, like maybe I want to rotate from 0 to 90 degrees, right? I can basically say, oh, just give full power until you reach 90 and then stop. But obviously it's a physical system, so things don't decelerate instantly, and also there is many other factors in play. So there's this whole branch of engineering that's called control theory, and this handles controlling motors, and actually not even just motors, but also controlling the temperature in your ovens, controlling your air conditioning or your heating, and many things like that. It's really common across the industry, and for FRC, it's basically just used to control motors and maybe a couple other things. So why automate I did that title wrong, but why automate the control of motors? And it can simplify the job for the driver. Again, we want to reduce the amount of things they can do, and it can also make smoother, more accurate control than a human. So if they're focusing on 10 things at once, obviously they're not going to be able to give it smooth and accurate control like a human, like the computer could. And then why not automate every motor? This is super important also. It's more failure points. So we're getting better and better at doing less um, less failure on sensors, but again, if a sensor fails, like my encoder reads the angle, and let's say it gets unplugged, it might still think it's on, and so it'll just basically give full power to the joint and just break itself. So again, some things you really want automate it to be automated, and other things it's like there's really no point. Like for climbing, the only thing they're focusing on is climbing, so obviously it can be manually controlled. And also the drivetrain, for most of it is going to be basically manually controlled. And again, it's time consuming to program and tune. You don't always have all the time in the world to mess with these systems. So how I'm going to talk about control theory to you is I'm going to give you different types of controllers, which are basically, I would think of them as a different way of controlling the motors. And I'm going to start from the most simple and go up to the most complex, but the most complex is going to have disadvantages also. There's a reason why we don't always go with the most complicated controller. This is the graph on the right that I'll be using to represent how the control is. The red line is where it's trying to reach. So if we say the bottom is 0 and the red line is 90 degrees, the blue line is where the mechanism is in real time, or was in real time. And yeah, this can be other units though. So it's not always angles. It could also, the motor powers a linear mechanism, and so then it could be in inches or something like that. A simple motor controller is basically kind of what I talked about before, which is just giving 100% or X output until you reach your point and then just stopping. And a big thing with that is that, again, the mechanism has inertia. This depends. Some mechanisms have more inertia depending on gear ratios and weights and counterbalancing and a lot of factors. But basically, usually it's going to overshoot the target if you see it actually maybe is trying to go to 90 and ended up going to 100. And so, yeah, sudden acceleration and deceleration. At the beginning, it just gave full power to the mechanism, which usually isn't too bad, but at the end, this would be kind of a harsh stop. Again, depending on the mechanism. A bang bang controller is a controller that is used in some cases, but the majority of cases, it's just really bad. Basically, it's the same thing where you give 100% or X output towards the target. Towards the target is the main thing. So you don't just like stop once you reach the target. It's like as soon as it's like, okay, I'm gonna give 100% in this direction. It's like, oh shoot, I'm gonna give 100% in this direction. Usually it'll just end up jerking the mechanism back and forth around the target position forever. So usually we don't use it. Sometimes it'll work, but probably not. So now a big step is a proportional controller. Basically what this means is we slow down, like it's like a bang bang controller where we give effort towards the target, but how much effort we give is proportional to how far away we are. So basically what ends up happening is at the beginning I'm going to give 100% effort because I'm the furthest away I could be, and then as I reach it, it slowly goes down to 0%. One thing you have to note about this is I added a variable, and so I'm going to talk about tuning. I think I mentioned it earlier. Basically what tuning means is I have to adjust this value called kp, which is just for proportional, basically constant, and kp is how much I will slow down or not slow down as I reach the target. And so it still has a hard acceleration because again at the beginning it's giving 100% effort. It reaches its goal but not perfectly accurate, and again you have to tune the kp. This is what the code would look like. Basically the target is the red line where I'm trying to reach. The current position is like, let's take a point in time right here at like 1 second. That would be blue dot. And so your air is how far away you are, and then the final motor output would be your air times your kp value. And so these three graphs are representative of different kp values. Again, this is a kp value could be 1,000 for one mechanism, and that's the good value, and 0.0001 for another, and that's the right value. Again, it all depends on gear ratios and how you write that out. But for our thinking, this is a overshoot, basically, but overall, this is more accurate than everything else we've had, and it does give smooth deceleration. Jeez. This one undershot, as you can see, this is a lower kp value, right? Because right here, it might still be giving motor output. It might be saying, go at 0.1% speed, but the motor has a minimum speed to rotate, so it ends up just stopping. And here, it just is a little bit higher value. Now, if I have too low a value, it'll just be this, but lower down and never get even close to the target. And if you have too high of a kp value, what ends up happening is it basically becomes a bang bang controller. If you notice, like if you had just made that one basically, actually that's not true. But if I just made this like infinity, then the output would end up getting maxed out at 100%. And so then it's just a bang bang controller. So our solution to this is to add another variable. So I'm going to be adding on, so I had a P controller or proportional controller, and I'm going to have a PD controller, proportional derivative controller. You might not know what a derivative is relatively, you don't have to. My thinking for a lot of this is you don't need to know the math, you just need to know how it works in the real world, and that's true for a lot of things, honestly. So what we can do is basically in the code, I'm just going to show you the code. I don't know how helpful this will be. We add another variable, which is last current is a position we were at last. So this is taking the rate of change, or the slope. So this will be relative to the slope, right? And now we add in this value. So we have air just like we did last time, and we have air times kp, but now we subtract derivative times kd. And so again, I have three graphs representative of different kd values. So you tune kp until you get something like this bang bang controller oscillating back and forth. Obviously not a kp of infinity, but something relatively high. And how I would like to say derivative works is it smooths out oscillations. These are called oscillations where it just goes back and forth around the target. Again, it still has hard acceleration. It reaches its goal a lot faster because you want something. See how this one took a lot longer to reach it even though it's more accurate? Both these did, whereas this one went a lot faster. I want this fast speed with this accuracy, and this is what PD allows. But the downside is obviously now I'm tuning two values and I just doubled or even quadrupled the amount of time it took to tune. So this is kind of the goal, where again you get that really fast acceleration and then you decelerate towards the target. And so this is a high KD value where you can think of the D value as pulling down the KP also.
So this is a really high KD value, it's pulling it down more, and this is a lower one. But either way, these two are acceptable because at some point you just have to come to the realization you're never going to have perfect accuracy. Do I need perfect accuracy? Do I need my joint to be 0.01 degrees accurate, or is it fine if I'm even a degree or 5 off? Because a lot of the time you can be 5 degrees off and it does not matter. And that's just kind of something you have to live with not being perfect. Really, PID or a lot of control theory, you can't be a perfectionist as much as you want to. Um, in the extreme case, this is what a really high KD value is. Usually, I like to start with a KD value that is 1/10 of KP. That's just kind of a good starting point, but it could be a lot lower. And so if you ever notice it's just like oscillations at the beginning, like way before you even reach their target, that's a high KD. I don't have a great mathematical explanation for you, but basically what's happening is the KP takes full control, and this slope is really high right here, and so the KD is like, no, 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 don't do that. And then the slope goes negative, so then KD has no control over everything, and KP has full control to take back, and yeah, you can see how that continues on forever. Again, this is the code. Uh, Last current equals current is just like because this isn't a loop and it's just keeping track of the slope basically between loops. Integral. This is something I really don't like using, but the official name of the controller I've been talking about, the PPD controller, is a PID controller. You're gonna hear a PID controller. So even if someone has a PD controller, they might call it a PID controller, and that's technically not what it is, but basically that's the main gist of things. You can think of a PD controller as a PID controller with a KI as 0. And so what this does is it adds integral to the other variables. The idea of what this does is that you have your KD ends up like this, and your integral will just inch it up that little bit or inch it down that little bit. But in reality, there's so many complications that KI adds that is almost useless for FRC. Other applications totally, but there's so many extra errors that it adds, and you have to add a bunch more values. Like just a PID controller usually will not work, and you have to add like 3 or more variables just to help control the KI. But if you really need it, it can be useful. Again, still has hard acceleration, reaches its goal just as fast, but again, you gain that accuracy where it's basically on the line. You can see here. There's other issues I can go into more depth if you guys are interested, but now you have to tune 3 values for a little bit more accuracy gains, which relatively don't matter that much. This is what a well-tuned KI does, or a good value. A low value will basically just not do anything. It'll just look a normal PD controller. And then an overly high value, or just honestly, this could be a mix of different cases. Not really a high value, but a little bit. I can't give you a great answer on that. But basically, what happens is the PD controller gets you to here, and then KI is like, okay, your value's been too far away for too long, I'm going to step you down, and then it really just takes forever, and this whole jitteriness is just useless, so I would recommend against it. Basically, I added this another variable called integral, and it combines all the error. So it's going to keep adding up error until you get high enough to have an effect. So KI is usually going to be extremely low, like 100th of KD or lower, usually. So how do you choose the right controller? How much accuracy do you need? Like I talked about, usually you need a lot less accuracy than you might originally think. How fast you need to get there? My main thing is I would way rather get there faster than accurately, because a lot of the time in FRC, speed is important, much more than accuracy. How important is the mechanism? Is it worth spending a lot of time to tune? Right? I mean, sometimes if I need a perfectly accurate turret to shoot into the goal, then I'll spend a lot of time tuning it because I need the accuracy and the speed, whereas something less important, who really cares? So you just got to spend your time wisely. Another thing to account is like how fragile is the mechanism, because some mechanisms I could kick it with my foot and it's fine, and some of them I could tap it with my finger and it falls apart. Or hopefully not. Hopefully we don't have those, but you get what I mean. Where some mechanisms can't handle super fast accelerations. Some examples is from our different robots. You can tell that our most favorite controller is PD, like I talked about, and that just works really well. Some tips that I would like to give you is start with big changes and then slowly work down, because you could end up going with slow changes from a starting value and then just ended up just taking forever. So start with big changes, kind of experiment with what happens, and then narrow down your results from there. Usually what you do is you start with tuning the P until you get the speed you want, but again, there's going to be some oscillations. Then take D as the starting value of a tenth of what your KP was, and then add I at a really low value until you're accurate enough. Again, this is something I would really recommend against. Also, for starting KP, basically you can like do the math of a KP control in your head right here, and just be like, okay, if the robot had an error, if it's 5 degrees away, then how much output do I want to give the motor? And you can just kind of, you might get a better sense for this in a bit, but basically you want to make sure that if you're 5 degrees away, you're not going to give 100% effort. You probably want to be giving like 10% effort, or it's really dependent on the system, but you kind of get what I'm saying. Okay. So, if you get stuck in an endless loop, it's best to just quit what you're doing and just completely restart. I think that's probably my best advice. Your mechanisms may not be able to be as fast and accurate as you want. Just sometimes you're just not physically capable of that because of how fast our control loops are running, and how good how variable the sensors are, and many other things like that. Here's some example values just for you to look at. I'm not going to put the mechanism with them, but just some ideas to kind of look at. Okay, other notes. Mechanisms with high gear ratios are a lot easier to tune. They have more fine control, so it takes basically more power. You have to give more power to turn it, less power to turn it, and so then it gives you a whole, like, let's say to move the mechanism at like, I don't know, 5 degrees a second, it'll take 0 to 20% effort, whereas with like a high gear ratio mechanism, it'll be like 0 to 1%, and you have very little control in there. It's a lot easier to tune if you have a stable mechanism, because if you have a fragile mechanism, they are very hard to tune, and I would highly recommend against trying to tune a fragile mechanism, especially if you're not really good at this. Don't try and fix mechanical issues with different controllers. If there's extra friction at one spot, fix it in the real world, because trying to fix it with code is never going to work. Trust me, I've tried this, other people have tried this, it does not work. Fix it IRL, and that's just what you have to do. And if you can't fix it, then you just have to live with a controller that's just not maybe what you want. Now again, we're trying to consolidate a lot of the class. So now I'm going to talk about extensions to PID. Usually PID is pretty good on its own, but we almost always, at least in 2020, add a lot of things on top of PID to make it more desirable. So the big thing is accounting for gravity. A lot of mechanisms, we don't have counterbalance. Basically, a counterbalance would be like a spring or something, so you could move it and it's like basically weightless, if that makes sense, but it still has like inertia and stuff. So what we usually do is we pull up Desmos, and we measure, okay, it takes, if I were to try to hold this mechanism at 0 degrees, it takes 10% effort to hold it there. And holding it at 90 takes 0% because it's like vertical, and then 180 is 10% in the opposite direction. And then you can just kind of form a curve with a regression in Desmos, and then you get an equation like this, and you can just add this to your output. So you have your PID controller or whatever, and then your final output would be the sum of whatever your PID output was plus what's called a feed forward output. Basically, the feed forward output is this equation we came up with from Desmos right in here, and current is basically x, if that makes sense, the x from this equation. And feed forward is basically just, it doesn't really care what the encoder's reading, although technically it does here, but it's not like a full feedback controller. I don't know how to explain that super well. Motion profiling, I've been talking before, a PD controller, you can't control acceleration. It has good deceleration if you make it that way, but always it's just basically just going to give 100% effort at the beginning, and some mechanisms can't handle that, or sometimes it's just nice to not do that, and then the mechanisms will last for longer. So motion profiling, instead of just controlling the position, I want to be at 0 degrees or 90 degrees, I can control the acceleration, velocity, and position all together. And so I can create super smooth movements. I can select the fastest cruise velocity to reach. So this is a graph of position over time. So if you notice, this is super smooth and ramps down. So I can control the slope of this is the max velocity. This is how fast I want to go. So obviously a slope like this would be a slower velocity, and then there's a certain max of how fast the mechanism can actually be moved. And then the slope of that, or the derivative of the derivative of that, is the acceleration. I can control that also. And then obviously you can control position. This is velocity over time, and if you notice, this, where the height of this is the max velocity, and then the slope of this is the acceleration. If you hear motion profiling, you will definitely see a trapezoid. This is called a trapezoidal motion profile. Kind of a complicated name, but it's really not that complicated. And it usually has a bit more accuracy. So it adds 2 more variables. Although these are not something, I talked about having a KP, KI, and KD. You have to tune these until you kind of adjust them until you get values of how you want to move your mechanism. Motion profiling, while it does add 2 variables, it's not something you have to tune. You can actually measure these values. You can measure how fast the mechanism can move, velocity-wise, and how fast it can accelerate, or how fast you're comfortable with it doing it. And then you can turn them down to your needs, but you're not really tuning them. And so there's a couple libraries here that do it, but I'm not going to get too much into that. This is something that it would look like that you might see, maybe not. Basically, this handles all of the PID and motion profiling for you. So basically, you make this new object with all your constants, and then you just call a function called calculate with my current position and my target position, and it'll return you an output with everything all together. This looks a little more complicated, although it isn't. Basically, these 4 lines just set my constants, like I talked about, and then this will just tell the motor controller to go to where it wants. Okay, so I've been talking about tuning KP and KD, and this is kind of something experimental. I'm not sure if we'll use this in the future. We did enjoy it in 2020, and only in 2020. Basically, this automatically calculates your gains. You give it full control of the robot, it'll move them around and do some insane math I personally don't even understand, and it's a lot faster to tune, and can give you more accurate control. It literally takes seconds to tune, even though it can be sometimes annoying to set up. It is something that we really liked. Basically, it gives you this whole window. Someone from WPI lib wrote up, or a couple of people wrote up this Python tool right here, and you write some code here, you deploy it, and then it gives you a bunch more values than you might be used to. So in the end, I'm going to end up having 7 variables just for one mechanism. I'm going to have my KP and KD that you talked about, the max velocity and max acceleration from motion profiling like I just talked about, and then it's going to add KS, KV, and KA. These are all called feed forward values like I talked about, and they don't care where your mechanism is, they're just going to be main default. And so this completely changes the way a PD controller works. Basically, KS is the minimum speed that you need to move your mechanism. So, if I apply 1% effort, the mechanism won't move, but then if I apply 3.275%, then it'll barely start, like, kind of inching forward. KV is the voltage, or sorry, this is minimum voltage needed to move the subsystem.
Again, voltage is you know, I've been talking about motor control and percentages, so 0 to 100%. Usually, voltage for a motor is 0 to 12 percent-ish, depending on the battery voltage at the time. kV is like, how much voltage do I need to reach a target velocity? If I want to reach 5 degrees a second, how much voltage do I need? And then Ka is how much voltage I need to reach that acceleration, which is the same thing for acceleration. Um, Basically, instead how this works is Ks, Kv, and Ka, I can say, I want to reach this velocity and this acceleration, and these values will calculate like 90% of where I want to go. Like if I just only had these three values, like they would get me to my target, just with not much accuracy because the voltage again changes like how charged the battery is or not. And so instead of working where Kp and Kd do all the work to get you there and to get you there accurately, these three values do all the effort of getting you there, and then Kp and Kd are this just kind of there to just minorly tweak it from where it is at. Basically, automatically calculates your gains, faster and more accurate control. It can, no matter what in the time span, and even sometimes not in the time span, it can just give you insanely accurate control. But it can be prone to unit errors, and it has a couple other things. But overall, the benefits um, greatly outweigh the downfalls, in my opinion. Okay. Yeah. Basically, what I talked about. Did I skip something? Um, just like I talked about with the profiled PID controller, it adds another class right here with three more values, and you add these to get your final motor output. That is it for the class. I have no idea how long this video is. I hope it's under 20 minutes, but um, I'm gonna hopefully make this as a reference on YouTube, and you can refer back to it because I'm assuming you can't remember all of that. But um, yeah, I think that's good for the class, and there's no practice problems because I can't really give practice problems on this stuff. The really hard part about trying to teach this online is that we can't. I need to give you. I need you to. I need you to tune a PID controller yourself to understand how to do it, but we cannot do that. So, PID I think is kind of an art, honestly, tuning it, and that's why I like using the auto tuner. Um, yeah, hopefully you guys will be able to catch up in person whenever that happens. Okay, peace out.